Hi, everybody. Thank you for joining. I'm excited to be here and see how many people are interested in machine learning and programming languages. This is a joint work with Mitai Zilberstein, Omer Levy, and Eran Yahav. As a motivating example, imagine that you're given this Python code, which has non-meaningful variable names such as P, C, O, and E. These names have could be given by an amateur programmer or have been deliberately renamed for obfuscation purposes. And you would like to predict meaningful names such as command, process, out, and red code that will help you understand and maintain this code. As another example, imagine that you're writing this JavaScript function, but you're not sure how to name it, and you would like to predict meaningful name, such as clone object, that will help your users find it and use it correctly. As a final example, imagine that you're copying the snippet of Java from Stack Overflow, but when you paste it in your project, you're not sure what is the full type of this connection class that you need to import. As a human, you might guess that it's either a MySQL JDBC connection or an Apache HTTP connection, where in fact, it's an H-based client connection. In the past, every programming language and task required a tailored solution of their own. This solution contained specific features, specific analyses, and learning algorithms. We present a representation that is so general that it works for multiple learning algorithms, many programming languages, and many tasks, and completely automatic. So the question is how to represent a program element. We look for a representation that should work for many programming languages, it should work for different tasks, and be useful in multiple learning algorithms. For example, let's take a look at this piece of code. It loops while not done, and if some condition is met, done is set to true. So as humans, we understand that done is a suitable name here, and that calling this variable count would be confusing. But the question is, what are the properties that make this done a done, rather than any other name, such as count? So the main idea is that the semantic role of a program element is the set of all the structured contexts in which it appears. Done is done because it appears in particular structured context. And we do that using AST paths. It's a general and simple method to represent code of any programming language in machine learning models. So given this piece of code, we parse it to get its AST, and then we extract all the AST paths that done participates in to be the features that represent done. Let's see an example to see why it makes sense. Let's take a look at one of those paths from these two occurrences of done, which are these two dones in the tree. And let's take a look at the path between them. This path tells us that done is a symbol reference, which is under negation, which is the condition of a while loop. Inside the while body, there's an if condition. If the if is met, there's an assignment in which the same symbol is assigned with a new value. So as you can see, this path tells us the whole story of done. It is both a stopping condition of a while loop with negation, and it is set to a new value if an if condition inside the while body is met. We represent this path as the sequence of its AST nodes, separated by up and down arrows, which indicate up and down movements in the tree. We then can feed the set of all of these paths, not only this one, as to a machine learning model, as the features that describe the true label done. As an example for a whole pipeline, given examples with good properties, or good names in this example, we parse them and extract paths. This blue path that we've seen in the previous slides is just one out of many. And then we feed those paths as the features of the true label done into a machine learning model. Then during test time, we're given a new example, which is not identical to the example that we've had before, but it does contain the pattern of while not, if, and assignment, this time with the name x. We then parse this example, extract paths, and this time we have a set of paths which is different than the set of paths that we had during training, but it does contain this blue path because it does contain the pattern. We can then feed those paths to the trained model, which makes a prediction given the combination of all of those paths. If the blue path was a significant enough feature, it will likely that the model will predict the name done instead of this x. So the advantages of this AST path representation are that it is expressive enough to capture any property that is expressed syntactically. It's independent of the programming language. It's automatically extractable. We only need a parser and a way to traverse the AST. It is not bound to the learning algorithm. And it works for different tasks. Basically, this representation can work with multiple learning algorithms. Thus, we wanted to take off-the-shelf algorithms, plug in our AST path representation, and see how the results change when the model is trained with different representations of the same input. Specifically, we experimented with conditional random fields, CRFs, and a variant of word2vec. I will explain in brief about each of them. So, JSNice by Raichev and colleagues was the first to use CRFs with programs. The CRF is a probabilistic graphical model that can be thought of as a graph in which the nodes are program elements such as done, true, and some condition. Some of them are constants that the model takes as given, and some of them are variables like done that the model tries to predict. The factors that connect those nodes are learned scoring functions that during training learn to assign a real valued score given the type of the factor and the values that it connects. So for example, this factor, which is of type symbol ref assigned true, is more likely to assign a higher score when the values that it connects are done and true, rather than count and true, for example, because done is more likely to be assigned with true than count. We use CRFs exactly in the same way as JSNice, except that we plugged in our AST paths, which are automatically extractable, instead of their factors. As for training with word2vec, we used a variant of word2vec that takes as input pairs of words in context. It's up to us how to define the context, which I will explain about shortly. The model trains and produces a set of word vectors and a set of context vectors for every word in context that it observed during training. Now for prediction, we've used the following simple algorithm. Given a set of context, we looked up for their vectors, summed their context vectors, and looked up for the word that is most similar in terms of cosine similarity with the summed context vector. So I'll repeat that. Given a set of context, we looked up for their vectors, we summed those context vectors, and then computed the cosine similarity between every word vector in the dictionary to the vector of the summed context. And then returned the word that maximized this cosine similarity. So as I said before, it's up to us in this model how to define the context. And specifically, we experimented with 3 types of context and trained a new model from scratch for every type of context on the same input. Each time the input was represented using a different context. So the first type of context was to use the neighbor tokens. This is the most straightforward approach, which is also common in NLP, in which the target is predicted given the surrounding tokens in the token stream, within a fixed window to the right and to the left. The second approach was to use the surrounding AST nodes. In this baseline, we predicted the target given the surrounding AST nodes within a fixed distance in the tree. And our approach was to use AST paths as context, which means that we used the same surrounding AST nodes, but also with the way they are related to the target, which means that the context was each surrounding AST node with the path between this node and the target. We evaluated our AST paths for 4 programming languages, Java, JavaScript, Python, and C#, for 3 tasks of predicting method names, predicting variable names, and predicting full types, and 2 learning algorithms, which were the CRFs and the word2vec variant. Here are some of the results for prediction of variable names with CRFs. So the vertical axis is the accuracy. The blue bars are the results of using AST paths in each language, and the orange bars are the baselines. So in JavaScript, we used as a baseline an Uglify.js, which is the open source version of JSNice. In Java, we hypothesized that n-grams with CRFs would be a strong baseline because of the rich type system that Java has, which often has a high correlation with variable names. And when we did not have a concrete baseline, like in Python, we used CRF with no relation, which means that all the factors were represented as the same constant symbol. So the model has learned to assign a score for every pair of values, regardless of the way they're related to each other. So as you can see, using AST paths improves over n-grams over existing systems like Unuglify.js, and has an even larger improvement over using no paths at all. Here are the results for the word2vec experiment. So using AST paths as the context of word2vec is the blue bar. As you can see, using AST paths almost has twice as high accuracy than using the surrounding nodes as context and using the neighbor tokens as context. Until now, I gave the impression that we take all the paths. But in fact, when training on millions of examples and extracting hundreds of paths from each example, a huge number of different paths are given to the learning algorithm. This makes training slow and memory consuming. So we experimented with different approaches for limiting the number of distinct paths. The first approach was to limit the paths by their max length and max width. We defined max length as the maximal distance in the tree that the path connects, and max width as the maximal difference between sibling nodes in the path. So for example, in JavaScript, limiting the max length from 7 to 6 reduced the number of distinct paths from 13 million to 11 millions. Reducing the max width from 3 to 2 reduced the number of distinct paths from 13 million to 12 millions. Another approach was to abstract the paths. We were wondering whether the whole representation of the path is needed with the whole sequence of nodes and the up and down arrows, or maybe we can keep only some of this information. For example, keep only the top node, the while node in this example. In this approach, the same number of paths were extracted from each example, but some of these paths were represented in the same way. This reduced the number of distinct paths to hundreds in this example of taking only the top node. Here are the results for limiting the max length and max width. So the vertical axis is the accuracy, and the horizontal axis is the max path length. Each curve here is a different value of max width. So as you can see, increasing the max width from 1 to 2 increases the accuracy across all lengths. Increasing the max width from 2 to 3 has a more minor improvement to the accuracy. And increasing the max length has a significant improvement until it saturates in JavaScript at around length of 7. And all of them, starting from a max length of 4, achieve a higher accuracy than Unuglify.js. Here are the results for the Obstructions experiments. So the vertical axis is, as before, the accuracy. The horizontal axis is the training time in hours. And each point here represents a different experiment in which the same model was trained on the same data, but with a different abstraction of its input. So the full point here represents the full representation with the whole sequence of nodes and the up and down arrows. No path represents using a single constant symbol for all of the paths. And in between them are the different abstractions. So for example, first, top, last is an abstraction that takes only the first, the top, and the last nodes in the path. So as you can see, using first, top, last, for example, achieved about 3% lower accuracy than using the full representation, but it also reduced the training time by about 60%. So these abstractions allow us to tune the trade-off between accuracy, training time, and memory consumption. Here's an example for a JavaScript function that counts something, and it has non-meaningful variable names. And our model predicted the names array, target, and count. This is actually a difficult example because there are no external APIs here that can be used as anchors. Here's an example in Java which sends a GET request. And our model predicted the names URL, client, request, user, response, entity, and result. In Java, sometimes the prediction is easier because we have the type, so a variable named client is more easily predicted given the type HTTP client. And we were also wondering what are the next candidates after the top prediction. So the top prediction in this example was done for the variable D, but when the next candidates after done all captured similar notions like ended, complete, found, finish, stop, end, and success, it increased our confidence that the model performs stable predictions and actually captured the semantic role of the element. So as you can see, using AST paths allow the model to actually learn by itself that done, ended, complete, found, finish, stop, end, and success are all similar in this context. In the same way, we extracted some other similarities, like rec is similar to request, count is similar to counter and total, element is similar to lm and l, etc. So to summarize, we see code representation as a trade-off between the learning effort that is put on the learning algorithm and the ability to generalize to other programming languages and tasks. Using the surface text is too noisy and puts a lot of effort on the learning algorithm because the learning algorithm implicitly needs to relearn syntactic and semantic regularities. Using more complex analyses, such as domain-specific languages, handcrafted syntactic features, semantic analysis, and using the dependence graph, these are all great, but the more complex they are, the more language-specific, task-specific they become, and they require more domain expertise. We see AST paths as the sweet spot between these two approaches. On the one hand, it is simple and easy, but much more effective than using the surface text. And if surface text can be learned using n-grams, we see AST paths as the structural n-grams. It's a strong and simple baseline that we think that should be used as a first starting point for every machine learning for code task. I'd love to take questions.
So how dependent is this on the actual AST you want to use? So imagine instead of
can you repeat that?
Yeah. So here you show like unary not, but what if I have chosen to just say unary and make the not another subtree? Does it make a difference the kind of AST that you choose for the representation?
It does matter, but once you train a model on examples that were parsed using the same parser, and you train on these kinds of paths, then on test time, you also observe the same kinds of paths. So the same parser needs to be used during training and test, but once you fix the parser, everything is automatic.
Hi, maybe I missed the intuition, but could you say a little bit about why you chose those particular models to use, and perhaps maybe comment on the complexity of the AST paths, because it seems like the problem size could be even handled by something simple like nearest neighbor.
So your first question was why did we pick those particular?
What's the intuition behind CRF and Word2Vec?
Actually, this AST path representation is just the representation. It can be used with any machine learning model that can handle such a large number of features. Specifically, we use CRF, which was shown by previous works to be very powerful, and the other algorithm of Word2Vec was just a simple algorithm, so such that the way we represent the context would be significant. But we could have done that with many other learning algorithms. And can you repeat your second question?
I guess the point of the AST path is to have a good encoding, right? To project down to a smaller dimensional space upon which you can then extract the features. I guess I'm asking, is that dimension, that small dimensional space already good enough to do your classification or your matching, right? Can you just do nearest neighbor search on an AST path to done?
Nearest neighbors is difficult because we're talking here about millions of examples. Each model was trained on millions of examples, and each example contained hundreds of paths possibly. So using nearest neighbors would be much more computationally expensive.
Well, it seems like that would be a storage problem, not a computation problem.
Both a storage and a memory limit, yes. But it's possible. The focus of this work is about the representation. This representation can work with nearest neighbors.
Thank you.
Your definition of AST path connect two occurrences of the same variable. Have you tried trying to connect more than two occurrences? For instance, if you have a variable named switch or mode, you expect to have more than just one assignment, and having several is important to finding a good name in that case.
Yeah, so in my example, I showed a path that connects two occurrences of the same variable, but we didn't take only those paths. We took paths between every two program elements in the program. So in the example that I showed before, there was also a path between done and true. These pairwise paths are just an abstraction of a more general idea of using n-wise paths. So we did consider using n-wise paths. It just was more complicated to run. And we also tried other types of paths like semi-paths, paths that don't begin and end in terminals, but start from a terminal and go up to its ancestors. So using AST paths is just the general idea. Practically, it worked best with pairwise and semi-paths.
Hey. Have you thought about different coding styles and naming conventions for different programming languages?
Can you repeat that?
Have you thought about different coding styles and naming conventions for different, I don't know, applications?
Yeah, well, the main assumption is that we train the models on a large enough corpus of data such that the main conventions will be learned. If a new example is now given to the model which has totally different naming conventions, then any machine learning model actually won't be able to predict this outlier. But we trained the models on the top projects in GitHub, which were hundreds and thousands of projects, and expected that the most common conventions will be captured.
Okay, so did you check the outliers? Did you check the outliers for these projects? I don't know, like...
We examined them manually. Most of the times they weren't that interesting. Sometimes there was a project which had like a weird name for a variable. There's nothing much we can do about it. There are some basic techniques of removing these outliers during training, like taking only names or paths that occurred at least 5 times, let's say. But these are standard techniques that can be used, but the main idea is that the model learns to capture the common conventions.
Right, thank you.
So any more questions? Okay, let's thank the speaker again.